You want to take a picture? I don't understand. Yeah, actually, perhaps this is closer to Mario, but not here. So let us resume with the second part of today's seminar series, mini-series. The second speaker lecturer is Pablo de Peria from La Plata, from Departamento de Matemática, Universidad Nacional de La Plata, and he will tell us a lot of interesting things about chordal and dually chordal graphs. So we will learn about some interesting duality there and how these graphs can be represented with trees.
Okay. Well, first of all, thanks for the invitation to the seminar. This talk is a survey on some results that I mostly obtained during my doctoral studies. And as the title says, it is about chordal and dually chordal graphs, which are classes that are defined, which can be characterized using trees, and those trees are closely related, so it will be mostly about comparing the trees of chordal graphs with the trees of dually chordal graphs. So let me give you a review about chordal graphs and dually chordal graphs. Well, the most basic definitions. A chord is an edge that connects two non-consecutive vertices of a cycle. So we can define a chordal graph as a graph such that every cycle of length 4 or more has a chord. For example, this is a chordal graph, and if we take this cycle, it has two chords. Chordal graphs can be characterized in a lot of ways, and one of those ways is using simplicial vertices. Vertex is simplicial when its neighborhood is a clique, that is a set of vertices that are pairwise adjacent, such that it is maximal. There is no other set of pairwise adjacent vertices that contains it. We define perfect elimination ordering as a sequence that contains all the vertices of the graph in a way that for each I between 1 and n, we are assuming here that the graph has n vertices. The vertex vi is simplicial in the graph and the subgraph induced by the vertices from vi to vm. So, for example, if we consider this graph, it has a couple of simplicial vertices, particularly this one at the left. So this vertex could be the first one of a perfect elimination ordering. To obtain the next vertices of a perfect elimination ordering, we consider the graph obtained by removing that vertex, and we again find a simplicial vertex. For example, this one. This vertex can be chosen to be V2. And we continue that way, selecting simplicial vertices after removing the ones that were already chosen, and we obtain the full perfect elimination ordering. So the characterization says that the graph is chordal if and only if it has a perfect elimination ordering. Well, another characterization of chordal graphs involves intersection graphs. The intersection graph of a family F has all the sets in F as vertices, and two of them are adjacent when they have non-empty intersection. Here is a small example of an intersection graph of these sets that you can see in the vertices. For example, 2, 3 is adjacent to 1, 2 because they share the 2, so the intersection is non-empty. Well, the characterization says that the graph is curved if and only if it is the intersection graph of a family of subtrees of a tree. For example, for this graph, this is a possible representation as a graph of intersection of subtrees of a tree. For example, 1 is adjacent to 3, and if we look at the representation of vertex 1 and vertex 3, they share this vertex. So they are really adjacent in the intersection graph. Well, the idea of how to obtain a representation of a chordal graph as an intersection graph of subtrees of a tree is related to perfect elimination orderings. Since chordal graphs have a perfect elimination ordering, we can construct them starting from a vertex and adding successively simplicial vertices. And if in each step we have a representation as the intersection graph of subtrees of a tree, we can obtain another representation in the next step. For example, suppose that it is not the whole graph and that it is just one step of the construction, and the next step of the construction involves adding this simplicial vertex. So what we do is considering all the vertices that are adjacent to it, and as this vertex is simplicial, all these vertices are pairwise adjacent. So they will be the subtrees that intersect pairwise. When we have subtrees in a tree that intersect pairwise, there is a property that says that they all share at least one common vertex. In this construction, 3, 4, and 5 share this vertex. So, to extend the construction in the next step, we add a new vertex and make it adjacent to that common vertex. And this vertex will be represented by the subtree consisting of only the vertex, and all the other subtrees are extended to that vertex to make it adjacent to the newly added vertex. So there are infinitely many representations for a chordal graph as intersection graph of subtrees of a tree, because, for example, one could add vertices to a representation that are not used, so we can have very large trees, but the idea is that we want simple representation, as simple as possible. So when the representation is not as simple as it could be, what we do is a reduction. The reduction consists of, in the case when we have a vertex which is adjacent to another, and each subtree that has that vertex also has the second vertex, what we do is to contract the edge to reduce the graph. For example, here we have that for this vertex there is only one subtree that contains it. So it is trivially true that any subtree that contains this vertex contains this vertex. That means that this vertex is redundant. It is not necessary really in the construction. So what we do is to contract this to make it a simple vertex, and this edge of the subtree that represented 1 also will be contracted in the same way. When we contract all the edges, we obtain something like this. What it happens is that when you consider one of these vertices in the reduced construction, for example this vertex, all the subtrees that have that vertex are all pairwise adjacent because they intersect. And it also happens that if you consider another vertex and again consider the subtrees that have that vertex, those subsets they don't contain each other. So, because if they contain each other, it means that this edge could be contracted to obtain an even simpler representation. So, the idea is that when we have the simplified version, for each vertex, it corresponds to one click of the graph, because the subtrees represent pairwise adjacent vertices, and because of what I said before, those sets are maxima, they are not contained in others. For that reason, we define the click tree. We say that the click tree of a graph G is a tree T whose vertices are the clicks of G, and such that for each vertex B of the graph, the set C sub B of clicks containing that vertex induces a subtree of T. This notation C sub B is very usual, and you will see it in many other parts of the presentation. So, well, we can also characterize chordal graphs by saying that the graph is chordal if and only if it has a click tree. And for example, if here we name the clicks and we make it correspond to vertices of the tree. For example, 1, 2, 3, 4 will correspond to the intersection of all the subtrees, which is this vertex, and we do the same for all the other clicks. What we obtain is a click tree because for each vertex of this graph, the set of clicks that contain that vertex is exactly the subtree that represented the vertex in the construction of the chordal graph as an intersection graph of subtrees of a tree. Well, this is related to the concept of click graph. The click graph of a graph is defined as the intersection graph of the clicks of it. That means that the vertices of the click graph of G, which is denoted K of G, are the clicks of the graph, and two clicks are adjacent when the intersection of them is non-empty. There is a property that says that when you have a connected graph G, which is chordal, any click tree of G is a spanning tree of the click graph. For example, if we consider this graph again, this is its click graph, and this is a spanning tree of the click graph, which turns out to be a click tree. For example, when we consider the clicks containing B, they are C1, C2, C3, C4, C5, which induce this subtree, and the clicks that contain I are C3, C4, C7, C8, and they induce this subtree. Well, there is another property that click trees satisfy, and it is the one that appears here. When we consider a click of the chordal graph, and we consider all the clicks that intersect that click, that also induces a subtree in the click tree. To see why, for example, let's consider the click C8. It has three vertices, H, I, and J. So any click intersecting C8 must be a click that has H, that has I, or that has J. The clicks that have J is only one, C8 itself. The clicks that contain H are C2, C3, C6, and C8, which induce a subtree because it is a click tree. the cliques that contain I are C3, C4, C7, C8, which induces this other subtree. And when we paint all the subtrees, the result is a larger subtree, because it is a subtree because all of them have C8. So we merge them to have a larger subtree. Well, because of this, we will start to get closer to dually chordal graphs. Another way to express this property is to say that for every vertex of the clique graph of G, the closed neighborhoods induce subtrees of any clique tree. And the definition of dually chordal graph is related to this. We define dually chordal graphs as the clique graph of chordal graphs. That is, a graph is dually chordal if it is the clique graph of some chordal graph. And we define a compatible tree for a graph G as a tree T such that every closed neighborhood of G induces a subtree of T. So, because of the property of the previous slide, every dually chordal graph has a compatible tree, because we take one chordal graph such that its clique graph is this dually chordal graph that we are considering, and we consider one clique tree of that chordal graph. We know that the neighborhoods, the closed neighborhoods, induce subtrees for the cliques, and then they are satisfying the definition of compatible tree. So every dually chordal graph has a compatible tree, and in fact, that provides us with a new characterization. A graph is dually chordal if and only if it has a compatible tree. Why they were called dually chordal graphs? To understand why it is useful to consider this property. We define a compatible tree as a tree such that every closed neighborhood induces a subtree. But they can also be defined as a tree such that every clique of the graph induces a subtree. The reason is these two equalities. When you take one clique, it is equal to the intersection of all the neighborhood of the vertices of that clique. And when you have a closed neighborhood, it is equal to the union of all the cliques that contain that vertex P. So if we have a tree such that every neighborhood induces a subtree, by this equality, the cliques will also induce subtree, because intersection of subtrees are also subtree. If we have a tree such that every clique induces a subtree, then by this equality, closed neighborhoods will also induce subtrees, because in this case we have the union of subtrees, all of them with a common vertex P. So the result is also a subtree. It also helps to define dual families. When we have a family of sets, the dual family will consist of these sets, which are constructed in the following way. We take a vertex V, and for each V, we consider all the sets of the family that contain that vertex V. And the result is one set of the dual family. So, with these properties and definitions, we can formulate characterizations of chordal and dually chordal graphs as follows. A graph is dually chordal if and only if there exists a tree such that every member of the family of cliques induces a subtree, and she is chordal if and only if there exists a tree such that every member of the dual of the clique family induces a subtree. Because remember that the definition of clique tree is a tree such that for every vertex, the cliques that contain that vertex induce subtree. But the cliques that contain a vertex is a member of the dual family for clique trees according to this definition. So this is the reason of the name, because we have the clique family in one and the dual in the other. Well, we also know that every clique tree of a graph, chordal graph, is a compatible tree of its clique graph, but there is one question: if the converse is true. Let's consider this example. We have considered before this clique tree, but now we have a slightly different tree, and this tree is a compatible tree for the clique graph. For example, the close neighborhood of C8 is still a subtree. But if we consider vertex D is in three cliques, C1, C2, C6, and what is induced by those three cliques is not a subtree, because this vertex is disconnected from the others. So we have here the example of a compatible tree for K of G, which is not a clique tree for the graph G. So this is a motivation to define the class of basic chordal graphs. A graph is basic chordal if it is chordal. The clique trees of G are exactly the compatible trees of K of G. So one of the first problems about basic chordal graphs could be the recognition problem. What can we do to decide if a graph is basic chordal or not? Fortunately, we have a characterization that is not very complicated. We need some definitions. We will call S of G to the family of minimal vertex separators of G. And for each separator, we define two families: C sub S, which consists of the cliques that contain that separator, and the family B sub S, that is constructed as follows. We consider all the cliques that intersect the separator, and one clique has to be can be in B sub S if it intersects all those cliques that intersect S. So for example, in this graph, let's consider the set 2, 5, which is a minimal vertex separator, for example, the vertices 4 and 3. So for that separator, C sub S is equal to C2 and C3. Those are the two elements of the set. And to find B sub S, we consider all the cliques that intersect the separator. We can see that any clique either has the vertex 2 or the vertex 5. So every clique intersects the separator. And which are the cliques that intersect all the separators? They are C2, C3, and C4. They intersect all the cliques, and C1 and C6 are excluded because they do not intersect. So B sub S is the set consisting of C2, C3, and C4. So we see that CS and DS are two different sets in this case. And actually, a graph is basic chordal if and only if B sub S and C sub S are equal for all the minimal vertex separators of the graph. So we go back. This is an example of a graph that is not basic chordal. But if we consider this other graph, which is different from the other because of the addition of these two edges, and we consider again 2, 5, it is still a minimal vertex separator of 3 and 4. When we consider V sub s for this graph, now the cliques that intersect 2, 5 are all of them except C6, 3, 8. And the cliques that intersect all the cliques except C6 are C2, C3, sure, they intersect all of them. C4, no, because it doesn't intersect C5. C5, no, by the same reason, of course, because of C4. C1, no, because it doesn't intersect C7. So the only remaining sets that intersect all the other cliques that I have mentioned are C2 and C3. So in this case, we have that V sub s is equal to C sub s. And if we revise all the other minimal vertex separator, like in this table, we could see that the equality between V sub s and C sub s is verified. So this is the example of a graph that is basic chordal. Well, if we want to continue studying basic chordal graph, it is convenient to define some new families. Since the definition of basic chordal graph involves clique trees and compatible trees, and the definition of clique tree and compatible tree is because of the existence of some sets that induce subtrees in them. We try to generalize those ideas by defining for a chordal graph G the family C of G that consists of all the sets that induce a subtree of every clique tree of G. So, for example, the set C sub B, by definition of clique tree, must be in this family. We define for a dually chordal graph the family SDC of G, similarly as the sets that induce a subtree of every compatible tree of G. The reason for the names is the S comes for subtrees and the other letters come from the name of the classes. C for chordal, DC for dually chordal. So examples of members in SDC of G are cliques and close neighborhoods, because we know that compatible trees can be characterized by the fact that cliques and close neighborhoods induce subtrees. And some other sets that are in SDC of G are minimal vertex separators, because actually compatible trees can also be characterized by the fact that all the minimal vertex separators induce subtrees in them. So with these definitions we can give a new characterization of basic chordal graph, and it says that the chordal graph G is basic chordal if and only if SC of G is equal to SDC of K of G, because if clique trees of G and compatible trees of K of G are the same, then the sets that induce subtrees in all of them must be the same, and the converse is also quite simple to prove. Now, if we want to study the structure of these families, it is useful to note, well, let's first define connected unions. We say that a union is connected when the intersection graph of all the sets that are in the union, the intersection graph of them is connected. That means that we can think of it as a union where we start with a set and then we unite it with another set that shares some vertices with it, and then we unite it with other vertex that shares with some of the previous ones, and so on. That is, it is a union when you can put a new set in the union, provided that it intersects some of the other ones that we already had. So, regarding connected unions, we can say that connected unions of members of S of C of G and S DC of G are also in those families, because if we have a sub-tree, and we unite it with another sub-tree that touches it, we obtain another sub-tree that is larger. So that's the reason that the unions, when they are connected, don't escape from the families. And these types of families, such that that are close under connected unions, can be characterized by the existence of a basis. We can define a basis for a family F close under connected unions as a minimal subfamily, such that every member of the family with cardinality larger than or equal to 2, with discarded case 1 because it is trivial, doesn't give us too much information. When those sets can be expressed as connected unions of members of B. One simple example of this could be considering the set 1, 2, 3, 4 and its power set. So all the sets that have 2 elements would form a basis for the power set of A. For example, when we consider the full set 1, 2, 3, 4, they can be expressed as the connected union of 1, 2, 2, 3, and 3, 4. And the union is connected because these share the 2 with this, and when we unite this third one, it shares the 3 with the second one. Well, the basis, when it exists, is always unique, and it consists of all the sets that cannot be expressed as connected unions of others. This would give us another characterization of basic chordal graphs, because we already know that for a basic chordal graph, a characterization says that a necessary and sufficient condition is that these 2 families are equal. But if these 2 families are equal, then they must have the same base, because a basis defines the family completely. When you know the basis, the family just consists of all the possible connected unions of those sets. Well, this can help us to study basic chordal graph if we are able to find this basis. For the case of a chordal graph, the base of S C of G consists of the sets C sub S. All the sets C sub S are in the basis. Remember that the set C sub S consisted of all the cliques containing that separator. And the basis of S DC of K of G consists of the sets B sub S. So it is not surprising that the first characterization that I gave about basic chordal graph say that the graph is basic chordal when B sub S was equal to C sub S for every minimal vertex separator. But sometimes we're in the case that we have a dually chordal graph, and we don't have a chordal graph such that the graph is equal to that dually chordal graph. So it would be useful to have another method to construct the basis for this dually chordal graph independently from the chordal graphs that can be used to obtain it. In that case, the basis can be obtained in the following way. We can take a 3T compatible, and for every edge UB of that tree, we will consider all the cliques that contain that edge, and we will intersect all those cliques. And that will give us a set of the basis. And when we do it for all the edges, we obtain basis, perhaps with some repetitions. There could be some edges that give the same set. It could be one problem that for a dually chordal graph there could be an exponential number of clicks, but this is not an obstacle because if we use neighborhoods instead of clicks, the result is the same. So the way to compute the basis for a dually chordal graph is not quite costly. So in this example, let's consider this graph that we already know that is not basic chordal, because when we consider the separator to phi, B sub s was different from C sub s. This is its click graph, which has two clicks. This is one click, C2, C3, C4, and C5, and this is another click, C1, C2, C3, and C4. Since both clicks have C2 in particular, this spanning tree of the click graph will be a compatible tree, because the subtrees that the clicks will induce are stars, because the tree itself is a star. When we consider this edge of the compatible tree, the only click containing that edge is C1, C2, C3, and C4. So by the method that I gave before, that should be one basic set for this dually chordal graph. But it is not a basic set for the basis of C of G, because there is no separator that is contained in C1, C2, C3, C4, because that was the way that basic sets for chordal graphs were obtained. There is no separator contained in all of them, by the simple fact that the intersection of all those four clicks is empty. So here we have another way to see that this graph is not basic chordal, using basic sets for each of them. Well, we define dually chordal graphs as the click graphs of chordal graph. So the question what is the family, the class of chordal graph, or the click graphs of chordal graph? It has a simple answer: dually chordal graphs by definition. But what about if the question now is, what is the class of click graphs of basic chordal graphs? To answer that question, we will use separating families. We say that a family is separating when, if for each vertex that is contained in a set of that family, the intersection of all the sets of the family that contain that vertex B is equal to the set which has a unique element, which is B itself. Well, when we know that, we can say that the click graphs of basic chordal graphs, despite of being just a subclass of chordal graphs, keeps being dually chordal graphs, and there is a construction that allows us to get, for a dually chordal graph G, all the basic chordal graphs such that their click graphs are equal to this graph G. For that purpose, what we have to do is to find a family F which is separating, which is contained in S, this C of G, that is, they must be sets that induce subtrees in all the compatible trees of the dually chordal graphs, and these sets must satisfy that they cover all the edges of the dually chordal graph. That means that when we consider any edge of the graph, there must be one set of this family containing that edge. And it is also true that when we consider these sets of the family, they must all be sets of pairwise adjacent vertices in V. So let's keep using this example. This is a chordal graph whose grip tree is this dually chordal graph, but we know that this is not a basic chordal graph. So if we wish to have instead a basic chordal graph whose split graph is equal to this one, we could consider this family, C1, C2, C3, C4, C4, which is one clique here, and for being a clique, it will induce a subtree of every compatible tree, so it satisfies this condition. By the same reason, we can use the other clique, and to ensure that the family is separated, we use single sets with one element. That is something that we can always do. We can always take the cliques of a graph, and it is sure that we will cover all the edges, because when we have one edge, it is always contained in one clique of the graph. So this tells us that this construction is not purely theoretical, it also gives us a practical way of constructing these basic chordal graphs. And if the cliques of this graph are too many, it is not necessary to use all of them. We can just use one clique per edge. That is, for each edge of the graph, we take one clique containing it, and that would be enough. So with this family, when we compute the intersection graph, we obtain this graph. So these two graphs are chordal. For both, its split graph is equal to this graph, but the difference is that this is not basic chordal, but this is basic chordal. Well, all these properties have some applications for some problems. For example, one problem about clique trees is the problem of the leaf phase. The leaf phase of a chordal graph is defined as the minimum number of leaves, that is vertices of degree 1, that a clique tree of the graph can have. For example, when we consider this chordal graph, we have this clique tree which tells us also that this is an interval graph because this is a path. When we have a tree with two leaves, this and this, we already know that there can't be another representation with fewer leaves. So in this case, when we can find a clique tree with just two leaves, it is sure that the leaf phase of the graph equals 2. This is an example. With respect to leaf phase, it can be computed polynomially because Aviv and Stachio found an algorithm to compute the leaf phase of any chordal graph in cubic time. So similarly, we could define the leaf phase of the dual leaf phase of a graph when G is dually chordal as the minimum number of leaves of a compatible tree of that graph. So if this problem can be efficiently solved, this also can be efficiently solved because for this dually chordal graph, we can take a basic chordal graph such that its clique graph is equal to G, and for that chordal graph, we can use this algorithm to compute its leaf phase, and it will also be the dual leaf phase of G because the clique trees of that basic chordal graph and the compatible trees of that graph G are the same, so the leaf phase, the minimum number of leaves in each case will be the same. So if we know how to compute the dual leaf phase of a graph, we can also solve this problem. Suppose that we have a graph G with at least 3 vertices, and we take a set A of vertices. We want to know if there is a compatible tree such that A is the set of leaves of that tree. Well, first we will start with one necessary condition, and the condition would be that all those vertices in A should be dominated by another vertex outside A. Dominated means that for that vertex B that we are considering, there is another vertex W such that the neighborhood of B is contained in the neighborhood of W. And the reason why we need this is because if we have a compatible tree whose leaves are the elements of A, then for each of those leaves we consider the only vertex adjacent to the leaf in the tree, and that by construction has to be a vertex outside A and that dominates the vertex. So first, to answer this question, we test this condition, and if that condition is satisfied, we construct a graph G star by adding for each vertex B in A vertex B star and the edge B star. And the solution to the problem is given by this theorem that says that there is a compatible tree with set of leaves equal to A if and only if the dual leafage of this graph G star is equal to the cardinality of the set A. And finally, there is another problem that can be solved using this theory, which is the problem of recognizing clique trees. That is, suppose that we are given a family T of trees. All those trees have the same set of vertices B, and we want to know if there is a chordal graph that has all those trees as its clique graphs. Well, the way to solve this is using the sets C sub S. The sets C sub S provide us with a new way to characterize clique trees. T is a clique tree of G if and only if C sub S induces a subtree for every minimal vertex separator S. And what's more, when we consider the graph consisting of the intersection graph of the family consisting of all the C sub S plus the unit set of cliques, that intersection graph has the same clique trees as G. So if we see that the sets C sub S are very important in determining the clique trees of a chordal graph. And what is really useful about that is that the set C sub S can be identified by looking at all the clique trees of a chordal graph without knowing the chordal graph itself. So that's the question, how to identify the set C sub S if we don't know the graph but we know its clique trees. Well, for that purpose, let's define for two vertices of a tree, A and B, T, A, B, the vertices only in the unit path of T from A to B. And if we don't have just one tree, but a family of three, we define it as the union of all the T of AB for all the T's that are in the family. For example, when we have this family of 4 trees, we consider the set 2, 3. In this case, it is equal the path to 2, 3. Here, 2, 1, 3, 2, 1, 3, 2, 3. So when we do the union, the result is just 1, 2, 3. And the result is that when we have a chordal graph and we have its family of click trees, and we select one tree of this of all these click trees, then the family C sub S can be obtained by using this type of sets where the two vertices that we use are the edges of the click tree that we are using. So this is purely in terms of the click tree as we want it, and so this allows the following construction. When we have a family T of trees and we want to know if it is the family of click trees of a chordal graph, we construct this family because these are the candidates to be the sets C sub S. And if this problem has a positive solution, then we know about one of the previous property that the graph formed by the set C sub S and the singletons should also be a solution. So if there is one solution to the problem, the intersection graph of this should be also one solution because it is supposed to be the set C sub S. And so the result says that the T is a family of click trees of a chordal graph if and only if this intersection graph is chordal, and the family of click trees of this graph has the cardinality of the family click trees. And testing the number of click trees of a graph is not complicated because there exists a formula. And a final example, when we have these four trees again, we use this tree as a reference, and for each of the edges of this tree, we construct the sets that we defined before that are supposed to be the candidates to be the sets C sub S. And when we form the intersection graph with them and the singletons, we obtain this graph that is our candidate graph to have these four trees as click trees. In this example, I don't test it by this condition of the cardinality, but by using another characterization of click trees that says that click trees are maximum weight spanning trees of the click graph when the weight of the edges is equal to the number of vertices that intersecting clicks share. For example, the vertex corresponding to the set 3, to the vertex 3 and 1 share these two vertices, so edge 1 and 3 has value 2. So there are two edges of value 2 and the other ones have weight 1, so obviously we want these two edges to be in the maximum weight spanning tree, and then we have to choose any other two edges in a way that the result is a tree. And for example, when we consider these two edges, we can choose only one of them because if we choose the two, we would have a cycle. We are obliged to choose one of them because we need to reach vertex 2. So we here have two options, and here we have two options, and in total we have four options, which when we analyze it just gives us the four click trees that we have above. Well, finally, the problem of determining if a family of tree is the family of compatible trees of a dually chordal graph is not equivalent. We could have families of trees that are click trees of a chordal graph, but that are not compatible trees of a dually chordal graph. But that would be an open problem to investigate if the complexity is more or less like the complexity of the recognition of click trees, or if the complexity is higher. Well, that's all.
Questions, comments? Koper. Do your results, probably some of the characterizations for basic chordal graphs, imply polynomial time recognition, or is it open?
Yes, yes. Because for a chordal graph, we have that the sets, the minimal vertex separators, and the clicks are bounded by the number of vertices. So finding the sets B sub S and C sub S is not complicated. So for each set S,
so C sub S.
So the worst algorithm that is testing in the simplest way is already a polynomial algorithm for recognizing.
Also for B sub S?
Yes, yes, because...
Yes, okay. The number is small, so we can just test.
Yes.
You compute C's first.
The exponent could increase perhaps from n squared to n cubed, but that's the worst thing that could happen.
And the other question I have is, so we've seen that chordal graphs are intersection graphs of subtrees of a tree, right?
Yes.
And in a special case, when the tree is a path, we get the interval graphs.
Yes.
Would it make sense to study click graphs of interval graphs? Has it been done? Is there any interesting theory there? So dually interval graphs, so to speak.
It's I think proper interval graphs.
So everything is known there, yes?
Yes.
Proper interval, hereditary class. And so
Yes.
Okay. Not such a rich theory perhaps, but better understood.
There are other classes, for example, DB and RDB graphs, which are constructed by adding more restrictions to the click trees, which imply giving orientations to the edges. There are some special types of click trees that give more restricted classes. And for those classes, there are dual classes, which can be obtained by using click graphs again, and they can also be characterized by a special type of compatible trees. So it is true that the theory can be repeated in subclasses, and I have done something on those classes, but well, the time was not enough.
Any other questions? So thanks again to both speakers.